Hi, my name is Paul from Physics High, and today I'm going to review the short answer responses for the 2021 Physics HSC paper. Now, like all of these sorts of questions, it is worth doing the questions before you continue. So either pause the video and have a go at the question yourself, or look at the link in the description below. I'll put the link to the actual physics paper for you to attempt it before you go. And before we start, please consider supporting me by buying me a coffee. To help support the work that I do, the link is in the description below. Let's get started. Now, first question deals with a DC motor. What we have here is a loop of wire within a magnetic field and of a certain dimensions. And we're asked two things. We're asked to work out the magnitude of the maximum torque produced. And secondly, we are asked to describe how the torque changes as the loop moves half rotation. So let's start off first of all by analyzing the diagram. Our torque is due to the formula torque being equal to BAIN sine theta. Now, what is theta? Now, theta is the angle between the magnetic field lines and the plane vector. So the plane vector is actually pointing upwards. Our magnetic field lines are going this way, and you can see we have now 90 degrees between those two, and so therefore, since it's 90 degrees in this position, our torque is actually at a maximum because sine 90 is 1, and so we just have BAIN to deal with. Now all we now need to do is substitute the values in, and you're going to get a value of 0.0392 Newton meters. So there's our maximum torque. It's asked for the magnitude, so we don't have to worry about the direction. The second part describes how the magnitude of the torque changes as the loop moves half a rotation from this position. So let's talk about the description. The best way to do this is as a graph. So we're going to draw a nice graph here, and what we're saying is, well, at this position, which is really at the 90-degree position, it's at a maximum like so. When it is vertical, in other words, the loop actually rotates in sort of that plane like so, my plane vector and my magnetic field are parallel, therefore the angle is 0, and therefore the torque is 0. So it's going to drop down to 0, and then as it continues to turn, it's going to go in the negative direction. However, we have a commutator here, and so that means that the torque will remain going in the same direction, and so as a result it's going to reach a maximum again up at this point. Now, being a sine relationship, we're going to get a sine component curve that looks something like this. Now remember, this value right here is actually at this sine 90 degree value, and this is the sine 180 degree, and this one is again at 90. So appreciate the fact that this is not sitting at an angle of 0 here. So that's a description of how the torque changes with respect to the angle change. All right, next question. It says a horizontal disc rotates at a constant rate as shown. 2 points on the disc X and Y are labeled. X is twice as far. So going from over here, we have a distance here of R, but a distance over here of 2r, and we're asked to compare the angular and instantaneous velocities of x with those of y. Now, the definition of our angular velocity is simply the change of the angle in radians with respect to time. Now, whether you're sitting at y or x, if you turn at any particular value, you turn at exactly the same angle. So therefore, when we're dealing with the angular velocities, and I would suggest that putting this as a table makes life easy. So if we look at their angular velocities, they are the same across the board. What about the linear velocity? Well, the linear velocity, which is equal to r omega, that is actually the formula for the linear velocity. Since omega stays the same, but r doubles, therefore x has twice the amount of velocity compared to y. And so therefore, that's the answer. Now, another way to look at this is also that velocity is equal to the complete circumference 2 pi r over t, which again shows you there is a linear relationship between the radius and the velocity, and so again the velocity at x must be twice that of the velocity y. Question 23, it says describe how Millikan and Thomson each use fields to determine the properties of the electron. Now I'm not going to write a full explanation of our answers here, but I'm going to highlight a couple of things. First of all, it says each used fields, and I make that point because you need to refer to two fields and then refer to the properties of the electrons. Now I'm not going to go into the full detail of Thomson and Millikan's work. I encourage you to watch my video on their respective works. But in essence, if we looked at Thomson, first of all, he used electric fields and he used magnetic fields. Now, in order to determine the velocity of the electron, he caused those fields to apply equal but opposite direction forces through the cathode ray tube. He thereby determined the velocity. Then by just using the magnetic field, he determined that they curved, and as a result determined a really important property, and that is the charge to mass ratio of the electron, which as a result of discovering that it was 1800 times larger than the charge to mass ratio of the smallest known atom, hydrogen, he was able to establish a new particle called the electron. What about Millikan? Well, Millikan determined the charge of an electron, and I'm going to put that straight away over here. But how did he do it? Well, he basically set up a field of oil droplets where he balanced the oil droplets so that they moved at a constant velocity. How? By applying an electric field and a gravitational field between the two. And since they're dropping at a constant velocity, and through calculations of the density of the oils and therefore was able to establish the charge on each of the droplets, and they were all multiples of a particular discrete value, which we now know as our charge of an electron, which is 1.6 by 10 to the negative 19 coulomb. So in other words, he was able to determine the charge of the electrons by balancing the fields between the electric field and the gravitational field. So now what we've done is we've determined the properties because they're different, and we've talked about multiple fields that each scientist used. And that's what you will need to do to get full 4 marks. Question 23, a stationary coil of 35 turns and a cross-sectional area of 0.02 square meters is placed between two electromagnets and connected to a voltmeter as shown. The electromagnets produce a uniform magnetic field of 0.15 Tesla through the coil, and the magnitude of the field is reduced to 0 at a constant rate over a period of 0.4 seconds. Calculate the EMF. Now, this is a simple question dealing with EMF. So our EMF is equal to negative because of Lenz's law, delta phi over delta t, the change of flux over the change of time. But what is flux, the change of flux? Well, it's the change in the magnetic field. So it's BA over delta t. Now, we now substitute everything in. So we get negative. Now, what is that change in magnetic field? That's what's changing. But if you look very carefully, it goes from 0.15 to 0. So therefore, we have negative 0.15 change in our magnetic field strength. We multiplied this by the area, which we told is remaining constant at 0.02 square meters, divided by the time, which is, of course, 0.4. So that's it, isn't it? Well, no, there is 35 turns. So all of this is magnified by a factor of 35. And so when you do the calculation, you're going to get a positive value, and the value becomes 0.2625 volts. And there's the answer. Question 25. A satellite is launched from the surface of Mars into an orbit that keeps it in directly position above the surface of Mars. Identify 2 energy changes as the satellite moves from the surface of Mars into orbit. Well, this is relatively straightforward. First of all, it is moving away from the Earth, so as a result, the gravitational energy has to increase. What about the kinetic energy? Well, it's going to be launched, is it not? So it's going to be launched, and it's going to have a velocity that is going to increase as it is launched. So simply put, the kinetic energy increases. The second question says calculate the orbital radius of the satellite. Well, in that case, you need to invoke Kepler's third law. So r cubed over t squared of my geostationary satellite, in this case around Mars, is going to be equal to gm over 4 pi squared. Now the thing we need to be mindful of course, is correct units. We need to work, of course, the radius, so we can rearrange that. So r cubed becomes equal to g m multiplied by t squared all over 4 pi squared. Now the thing you need to be mindful of is correct SI units. 24 hours and 40 minutes is 88,800 seconds. So if you substitute everything in, you're going to get a value of r, once you've cube root the answer, 2.04 by 10 to the power of 7 meters. Question 26. A student performs an experiment to measure Planck's constant h using a device that emits specific frequencies of light. When specific voltages are applied, the voltage V needed to produce each frequency F is given by this formula, where Q is the charge of an electron. Data is provided here, and here is a graph. So this is actually a skills of graphing. Now you're only given a non-labeled axis, so the best thing is to draw the graph in such a way that you get the maximum value. So the best option, if you look at your voltage over here, we've got 1.3 to 2.6. It makes sense to start this at 0 and then go 1, 2, and 3. Along our x-axis, our frequency starts basically at 5.3 and finishes at 7. So it makes sense to actually start at 3 and then go 4, 5, 6, and 7. You now just need to plot the points, and you're going to do this. Now that you've done that, it's just drawing a line of best fit. And that's basically it. Now part B is the student proposes using a data point 1 to calculate the value for Planck's constant, justify a better method from the experimental data provided. Now as teachers, we consistently try to drum into our senior students that by plotting data points and determining the slope to measure certain values is much better than reading the particular data points. So for example, in this case, by choosing, let's say, my first value, in this case, it's actually not even sitting on my line of best fit. Why do we do a line of best fit? Because it gives us actually the averages of all the values. Because in order this formula, you can see that V is equal to H over Q multiplied by F. In other words, according to my line, this is a linear trend. And so that although I can substitute values in here, by actually having multiple values and drawing a line of best fit, I actually am averaging out my results. That means a greater reliability in my results. So the slope here of my line, M, is equal to H over QE, and therefore if you determine the slope, you can then multiply that by the charge of the electron to work out H. Now you don't have to do this, but that is the better methodology, by doing the slope of the line to increase the reliability of the experiment. Question 27. A student is considering how to levitate a thin metal rod in a strong magnetic field of 1.2 Tesla. The current flowing through the rod will be 2.3 amps. And it says use a label diagram to show a suitable orientation of the current and the magnetic field to achieve this outcome. Include relevant forces in your diagram. So now you have to do some sort of thinking and saying, okay, I need to have a force that opposes the force due to gravity on my rod. So I want a force to act in the I want a force in terms of the magnetic field to act in the upward direction so that it counteracts the force due to gravity in the downward direction. And the best way to do this is to have a magnet like so on either side to produce a lovely linear magnetic field from, in this case, from left to right. Now I want a force in the upward direction. So if I have, in the case over here, I have my magnetic field heading from that direction, as you can see it. That's this situation over here, like this. It's a bit hard for me to do it with my right hand from this perspective. Then as a result, I want a force in the upward direction. So you can see I want my wire to therefore have a current going out of the page. That will mean I will get a force on this in the upward direction, and this is the force due to the magnetic field. as a result, or often referred to as the Lorentz force in the upward direction. But of course that counteracts the force due to the gravitational field. Now this is labeled, so what we want here is our magnets, right? It's already labeled as north. This of course here is my magnetic field, and this is obviously here my current going out of the page, though I have already stipulated by that putting that dot there. So now we need to explain why the mass per unit length cannot exceed 0.282 kilogram per meter. Well, what's going on? Again, we have basically two forces at play here. We have the force due to the motor effect, which is equal to BIL, and that is equal to our weight. And so therefore that's going to be mg. Now we want this at a maximum. In other words, if our weight is greater than BIL, the rod is going to drop. And how do we show that? Well, let's rearrange that, because what we want is the mass per unit length. So in other words, we divide both sides by L and we divide both sides by G. So what I get is BI over G, I move the G across, is equal to M over L. So what I have here on the right hand side is mass per unit length when I calculate this out. Again, now what we need to do is just substitute the values in, and I'm going to get my value of 0.282 kilograms per meter. So there is my value. That is going to be the greatest value that I'm allowed to have. Any greater, it's going to drop. Question 28. Now this is a 5-mark question, so we're starting to get a little bit more involved. A spaceship travels a distant star at a constant speed v. When it arrives, 15 years later have passed on Earth, but 9.4 years have passed for an astronaut on the spaceship. What is the distance? And then outline how special relativity imposes a limitation on the maximum velocity of the spaceship. The fact that it's worth 3 marks tells us it's a little bit more involved, because we are given time, not distance. So the first thing we need to appreciate is the fact that there is time dilation going on. On Earth, it's 15 years. On the spaceship, it's 9.4 years. So that basically means that the time dilation time, that is, we are seeing it outside the frame of reference of the spaceship, is our 15, but proper time for the astronaut is 9.4 years. Now what does that mean, what we can work out? Well, that means we can work out the velocity, because TV is equal to T naught over the square root of 1 minus v squared over c squared. Now I'm going to make this actually equal to T naught over 1 minus x squared, where that x becomes our fraction of the speed of light. So if I rearrange that formula and substitute that in, I'm going to get, and then my x as a result becomes 0.78. The velocity ends up being 0.78 times the speed of light. We now know the speed of our spaceship. We now can work out the distance, remembering that our displacement is equal to the velocity multiplied by the time. Well, the velocity is 0.78 c. Notice I'm using here my relationship with the speed of light. I multiply this by my time, but remember this is a time that the observer has, so that becomes 15, and this is 15 years. So the fact that I'm using a relationship of the speed of light, and this is years, the distance I'm going to get is actually going to be in light years. And so I end up getting an answer of 11.7 light years as my answer. So now we have to outline how special relativity imposes a limitation on the maximum velocity of the spaceship. Now, we know that as my velocity approaches the speed of light, there are a number of things that are going to happen. We've already discussed. First of all, we have length contraction. We have, of course, time dilation. But we also have what we call momentum dilation. And that formula is that the momentum of a particle as it approaches the speed of light is due to momentum dilation, where you have this formula, 1 minus v squared over c squared. Now what does that mean? That means as a spaceship puts energy into the rocket due to the burning of the fuel or whatever propulsion system that they use, they want to convert that into the kinetic energy. But the problem there is that that kinetic energy is composite of both the mass and the velocity, and there is actually a mathematical relationship between the kinetic energy and the momentum. It's not just going into the velocity. And so one way to think about it is this: if v squared approaches c, what happens to the momentum of my object? Well, if I put my values in and I actually put the maximum in, what I'm going to get is my momentum final result will be the square root of 1 minus c squared over c squared, which is 1, which is going to give me an actual 0. I'm going to get p naught over 0, and of course that's infinite. That's not possible. So what we're saying here is that object, any object with mass and velocity, in other words momentum, will not be able to attain the speed of light. Only particles that have no mass can attain the speed of light, and that of course are things such as photons. Question 29. Bohr, de Broglie and Schrödinger each proposed a model for the structure of the atom. How does the nature of the electron proposed in three models differ? Now the best way to set this out is as a table, and I'm going to do very simply the words, and if you want the details of the three, then I would suggest that you look at my video. So let's go through it. First of all, what can we say about Bohr in terms of how he defined electrons? Well, first of all, they are defined as particles. What are de Broglie? Well, they're actually defined as waves. What about Schrödinger? Well, he also talked about waves, but we're going to see how that's different in a moment. Secondly, in terms of Bohr, they have discrete energy, but they are particles nonetheless in discrete orbits. Whereas de Broglie? Well, de Broglie talked about waves, in this case talking about standing waves. In other words, de Broglie modified Bohr's model by saying, look, I can give a reason why they are in discrete orbits if we treat them as standing waves, not as particles. So I've already now differentiated between Bohr and de Broglie in that Bohr talked about particles, de Broglie talked about waves. But Schrödinger took this waves analogy a bit further. He developed what we call a wave function, and that wave function refers to the electron not in terms of a standing wave, but of an electron cloud. And that electron cloud is a cloud due to basically probability. Now, it wasn't just Schrödinger, it was also Max Born, but in essence the model changes. Rather than a standing wave or discrete orbit, we have basically an electron that can be described as the probability of finding it at a particular point. So therefore we have a far more robust understanding of the electron in terms of where we can describe its location in terms of, at least as a probability. The other important factor is that Bohr and de Broglie really only referred to the concept of hydrogen. That was easy to explain in that sense. However, Schrödinger combined the fact that this model can be used to describe any atom and the electrons with around its nucleus. Question number 30. An experiment, a proton accelerates from rest between parallel charged plates. The spacing of the plates is 12 centimeters and the proton is initially positioned at an equal distance from both plates. And the electrical potential energy of a proton is recorded in the following graph for the first 5 centimeters of its motion. On the graph, sketch the corresponding kinetic energy of the proton, and then the experiment is repeated using an electron. We need to describe how the motion would differ to that of the proton. Well, the first thing is to understand the conservation of energy. And the conservation of energy suggests that the total energy remains the same. And that means if I were to examine the potential energy as well as the kinetic energy of my proton, because my proton will speed up, it will accelerate, then the total energy must remain the same. Now we're told here the total energy right at the beginning is only potential energy because it's stationary. So my total energy must always be equal to this value. My total energy must always be equal to this value up here. But that means if I already have a unit of 1 for potential, therefore the difference here is the kinetic, and so therefore the kinetic energy at this point must be equal to 3. At this point my kinetic energy is equal to 0. And because the drop here is constant and we also have an increase that is also constant in terms of its energy, we should have a straight line between these 2 points like so. So there is our kinetic energy. The next point is explain the motion of the electron. How would it differ to that of the proton. The proton is significantly heavier than the electron, and so therefore the force that the proton experiences due to the plate will cause the electron to move at a much greater rate. So therefore the acceleration of my electron is significantly greater than the acceleration of my proton. In other words, it will move at a much greater rate, and therefore it will strike the plate at a much higher velocity due to the acceleration being different. So that's the first thing. But remember, this is an electron. So the fact is that whereas the proton, due to this field, is going to be moving in a downward direction, my electron, being opposite in charge, is going to move in an upward direction. So there is the other aspect of the motion. So the first one, I've related this to the mass. I've explained it. It's due to the mass difference that the acceleration is differently. But the charge difference is going to determine the direction of the motion of the electron and the proton, and therefore I've explained why they would move in opposite directions. Question 31. Two identical solenoids are mounted on carts as shown. Each solenoid is connected to a galvanometer, and the solenoid on cart 1 is also connected to an open switch and a battery. The total mass of cart 1 is twice that of cart 2. Explain cause and effect. What would be observed when the switch on the cart is closed, and on your answer refer to the current in each galvanometer and the initial movement of the carts. Now this is a 7-mark question, and so I could write up a really long-winded response here. Being 7 marks doesn't mean you need to take 12 minutes to actually answer this question, but I am going to highlight some key points and hopefully will illuminate the idea of how this question will be answered. Now, I want to examine two aspects. I want to examine the idea of what happens in terms of its motion, so the forces and its motion. And secondly, I want to highlight the idea of the galvanometer. So I'm just going to put F and G there, understand what I'm talking about here. So this is about the force, and this is basically about the galvanometer. And in essence, it's about electromagnetic induction. But I also want to talk about this in terms of identifying what's going on, then describing what's going on, and then explaining. So the first thing I want to highlight is that when the switch is turned on, what we will see initially is they will both be pushed away. So they will repel. That's all I'm going to say at this stage. The galvanometer is that we will see a change. The galvanometer will basically, they will both move. That is at the very essence a simplistic description of what's going on, but we need to go further. The description in terms of the movement is that you will find that the acceleration of cart 2 will be twice that of the acceleration of cart 1. Again, I'll talk about the explanation in the moment, but certainly cart 2 will move twice as fast initially than cart 1. What about the galvanometer? Well, the galvanometer in terms of 1 will basically stay on, whereas galvanometer 2 will go on briefly, but then go off after that. And it'll also be in the opposite direction of galvanometer 1. So now I've identified it and I have described it, but now let's go into the explain, and hopefully this will put this question all together. When the galvanometer goes on, we start producing a magnetic field here, and therefore the second coil will experience a electromagnetic change. Therefore, due to Lenz's law, will result in a repulsion of the forces. So therefore, automatically you'll see that I have invoked the idea of an EMF being generated, which is equal to delta phi over delta t, and Lenz's law also mentioned. These are the things you have to mention in your explanation. But now we have the two experiencing mutual forces. Now we are invoking Newton's third law as well. And because they experience the same force but in opposite directions, therefore, because cart 2 is twice as light, it's lighter than cart 1, therefore the acceleration of cart 2 is going to be twice as much. So I've now invoked the second law as well. So the explanation of the motion is tying in EMF, Lenz's law, the third law, and the second law. But what about the galvanometer? Well, obviously, due to Ohm's law, we're just going to have a consistent current. We have a voltage supply, we have some sort of resistance over here, and so we'll have a constant current. So what's going to happen to GT as it moves away? Well, initially, due to Lenz's law, that needle is going to go backwards in the opposite direction. So you're going to have G2 going back. But of course, that's going to only be momentary. It's now going to start to fluctuate back to zero, but because it's moving away from the cart 1, it's still experiencing a changing flux, a weakening change of flux. So initially what will happen is it will flick one way, then throw the other way due to the changing flux that it's experiencing as it moves away, and then it will again go to zero. So in essence, the needle moves backwards and a little bit forwards, but then to zero, which is in contrast to what G1 does, where it remains fixed at a constant current. Question number 32. Two students perform an investigation with a piece of elastic laid out straight on a table. The elastic is fixed at one end and has 3 markings at regular intervals. The distance between each marking is fixed, D1, D2, and D3. Pulls the elastic and new values of D1 and D2 are recorded and they are all doubled. And how well do these observations from the investigation model the evidence that led to Hubble's discovery of the expansion of the universe? In terms of our model, it's actually a pretty good model. First of all, that the elastic distances are stretched. So this idea of our stretching of our rubber band relates to the expansion of the universe. So that's the first thing that is good about this model. Secondly, you can relate is that further objects move more, or in other words, they are faster. The idea is that the velocities of galaxies are faster further away. So again, that models Hubble's, and it's not just Hubble by the way, but there have been other scientists who discuss this around the same time. But you clearly have a relationship here of further distance galaxies are moving faster, and we see that via the redshift. The third aspect is that the fact that it is doubled shows that there is a linear relationship invoked here, and that is consistent with Hubble-Lemaitre law, and it is the Hubble-Lemaitre law, and that it simply says that if you have your distance and your velocity, you have a linear relationship. The velocity doubles if the distance doubles, so to speak, at these huge expanses. So those actually are 3 things you can highlight as a good elaboration of the model that is represented here. Are there limitations? Like any model, there are limitations. The first limitation is that the sizes here are not correct. So in other words, our galaxies are infinitesimally small to the huge distances we are talking about here. And so the expansion that we measure is over those very large distances. So as you stretch this, those dots will increase in size. Relatively speaking, that's not what we see. The galaxies are practically the same size, and it's the space in between them that is expanding. The second limitation in this model, this is a one-dimensional model, when in reality, of course, we have a 4-dimensional model of space-time. So that is a limitation of the model. And so I've justified my answers of why that is good and why there may be 1 or 2 limitations. So now we come to question 33, which is a 9-mark question, and so quite involved, but it is an opportunity for you to display what you understand. And in essence, what we have here is 2 experimental setups, one to deal with a double slit experiment and the other to seem to be appearing to be something to do with the photoelectric effect. And we're asked, how do these results from experiment A and experiment B support 2 different models of light? In your answer, include a quantitative analysis of each experiment. Now to do this, what I'm going to do is I'm going to reduce the size of my question so I can elaborate a little bit further. So we're going to start off from the very basic and continue to build upon that so that you have a fulsome understanding of the question and how to answer this question, because really what this is all about is able to explain the concepts thoroughly, which includes the quantitative analysis. Let's start off with the really basic, and the first thing of course is that this experiment, the one that we have with the double slit, is our diffraction experiment. This diffraction experiment works on the basis, as you've seen in a previous question in this paper, that it's about interference and diffraction. So we have constructive interference producing bright spots and destructive interference causing dark spots. And so that in essence is a fundamental aspect of waves. Interference is a property of waves alone. And so that's the first particular point. Diffraction leads to our understanding that it is a wave phenomena. Well, what about our second experiment? Well, our second experiment is all about the photoelectric effect. And in there you have light arriving at 400 nanometers, but they're arriving as photons because the electrons that are emitted can only be emitted if they receive one photon, and whether they are emitted or not is dependent on the frequency of that photon. But for every photon we have only one electron, and it can never be anything else. So in essence, the photoelectric effect is really ultimately all about the particle nature of light. So if that's all you say, you are actually making an indication that you understand the difference between these two particular experiments. So we need to go a bit further. Why are we getting constructive interference? Well, in essence, what we have is two light paths basically coming from different slits that are meeting, in this case in our first bright spot, at a particular value such that the path difference between these two paths is equal to a single wavelength. And of course this here represents the angle here. And so that means we have a mathematical relationship that ties in the angle. So basically D, which is the separation between the two slits, multiplied by the sine of the angle, which is the part, basically the angle between the two paths, is equal to m lambda, and in this case lambda of course is the wavelength and m is the particular bright spot we have. Now we're only interested in the first one, so I'm now elaborating on the whole process of diffraction. But we're also asked for a quantitative analysis, and if you'll notice that the distance to the screen is 3 meters, that means the actual separation of the central maximum to the next maximum we can label as y. And so if I then rewrite that, I have y divided by the distance, which is our case our 3 meters. Well, that is equal to tan theta. But at these great distances and these small angles, this approximates to sine theta, which means I can now replace the sine theta with this particular value of y over 3. You see, now I have the ability to work out what y is because I know d and I know lambda. And so what I get is y over 3, which is our sine theta, is equal to, now m is 1 in our case, and we have lambda, which is that value, divided by d, and of course lambda is 400 nanometers, so that's 400 by 10 to the power of negative 9, divided by d, which is 5 by 10 to the negative 5, and you can see I can now work out y, and if you do the calculations you'll get y is equal to 2.4 centimeters. So in other words, I'm showing a thorough understanding of the process of what's going on here, diffraction, interference, a property of waves alone, and I'm now showing that I can use this understanding to work out the separation between two bright maxima. But what about the PE effect? It's a particle effect, as I've already stated, but I need to show a further understanding. Well, the electrons that are emitted have a certain amount of kinetic energy, and that of course is equal to the energy that they receive in terms of the photons minus the work function. And so by me elaborating this, I'm saying they receive a certain photon, they obviously need to overcome the certain amount of energy that's holding the photoelectrons in place in the metal. But if it's greater, the kinetic energy can be determined of my electrons. Now in this case, we can do some further calculations. Well, first of all, we are told that it's 400 nanometers of light. So what do we say? Well, can I work at the frequency? I can, because lambda, of course, is equaling to 400 nanometers. So the frequency is simply equal to c over lambda, and you can do the calculation. You're going to get 7.5 by 10 to the power of 14 hertz. Now I have the ability to work out this energy. So my energy of my photon, which is equal to hf, you can do the calculation yourself, you're going to get 4.97 by 10 to the power of negative 19 joules. Now compare that to the work functions of nickel and cadmium. You'll see that the one of nickel is higher than the value I've got here, and that's the reason why we're not getting any photoelectrons emitted, and you need to refer to that in your exam. That is, this value is not enough to allow the photoelectrons to be emitted. But the second one, calcium, has a value that is less than that. So I can actually work out the kinetic energy of my photoelectrons, because it's the difference between the energy that they receive, subtract, of course, the work function for calcium, which is 4.6 by 10 to the power of negative 19, and I get a grand total of 3.7 by 10 to the power of negative 20 joules. So now I've shown a thorough understanding of the photoelectric effect, as it is showing a particle-like property of light in this case. So that's answering the question, but I've supported the model and I've included a quantitative analysis. Let's have a look at our last question, and in this case we see a projectile motion problem. We have a ball that is thrown off a cliff and it lands to the ground, and we're given the value of the kinetic energy, and we're given three kinetic energy values with respect to time, T0, T1, T2. And we're asked, first of all, account for the relative values of the kinetic energy at T0, T1 and T2. What I'm going to do is I'm going to put a table together, and we're going to concentrate first on the kinetic energy at T0, T1 and T2. And of course we can put those values in and we get 864 here, 284 and 1393. But what other energy does it have? Well, it has potential energy. But do we know what those values are? Well, we can work that out, and this is where we're accounting for this. So we know that when it lands on the ground, the total energy, kinetic energy in this case, is 1393, but it's hit the ground, so the potential energy at this point is 0. So automatically we can now say that the total energy is the sum of those two, which is 1393. But of course, conservation of energy says it's going to be the same value for all three positions. It's 1393. And as a result, we can work out the potential energy in those other two places. We're going to get 529 here and 1109 here. But now let's account for what's going on. Well, the object is on a cliff, so it has both potential energy and kinetic energy. It's being launched up, so it gains in potential energy, which means it must result in a drop of kinetic energy. That's what we see at T1. It then falls, it loses all that potential energy, which must result in a gain in kinetic energy, but it falls further than the original height, so therefore it has an increase in kinetic energy, which we've related here. But we can take one step further. We can also look at it from a projectile motion problem. That is, can I work out the velocity of these three situations? And I can, because the velocity is equal to the square root of 2k over m. Now I've just rearranged the kinetic energy formula. And if you work that out, you can get these values. You'll get 24 meters per second for this particular value. You're going to get 13.76 for this one, and you're going to get 30.5 meters per second here. Now let's account for it. It's launched up. It's launched up with a particular velocity. It goes up, it must slow down because of the gravitational field, but it's moving horizontally still the whole time. And we know that is going to be 13.76. This actually ends up being the horizontal velocity, which remains constant throughout the whole journey. But of course it's falling down, so gravity will cause it to accelerate, increase in its velocity, which of course results in an increase in kinetic energy. That's why its maximum kinetic energy is determined by the maximum velocity at which it hits the ground, which is this. Now what about part B? Part B says the horizontal component of the velocity of the mass during its flight is 13.76. It says calculate the time of flight for these masses. So now let's have a look at this. What we need to work out the time, well, if we know in at least the vertical direction it goes up and down, we don't have to worry about the horizontal motion, just the vertical aspect. So what do we need to work out a time? Well, we need final velocity, we need initial velocity, we need acceleration and time. If I can work out the initial velocity in the vertical and the final velocity in the vertical, I already know the acceleration, it's 9.8 meters per second squared downwards. I can work out the time. But how do I work out the velocity? Well, we already have the velocities in terms of what their true velocity is. What we need is just the vertical component. Well, okay. So if a velocity has any direction, then its horizontal velocity and its vertical velocity will result in its effective velocity at some sort of angle. But we have the horizontal velocity, and that's 13.76. It doesn't change. It's the same at the beginning and at the end. If we look at the velocity at the beginning, I've already established it was 24 meters per second. I now can use Pythagoras to work out the vertical component. So the initial velocity ends up being the square root of 24 squared minus 13.76 squared. That ends up being 19.67 meters per second. Now I can do the same for the final velocity because I've already worked out the velocity when it lands, but all I need to do is the same idea. Of course, in this case, it's in the downward direction at 30.5. We know the horizontal component is 13.76, so I can work out this final velocity, and if you do the mathematics, that final velocity ends up being 27.19 meters per second, but of course it's in the downward direction, so that's a negative value. Our acceleration is negative 9.8 meters per second squared. I can now work out time. How? Because of v equals u plus at. All I need to do is substitute those values in, and you can do the mathematics, but you'll get a time of 4.78 seconds. There's the answer. And now we get to our final question. We have a spacecraft. It's powered by a radioisotope generator. In this case, we've got Pu-238 in a generator undergoes alpha decay, releasing energy. And the decay shows with the mass of each species in the atomic mass units. And we have those values. And we're asked two things. First is to show that the energy released by one decay is 9 by 10 to the negative 13 joules. And then what we're going to do is basically, knowing the half-life of Pu-238, we calculate the total energy produced by the generator during the first 10 years after launch. So let's start first of all with part A. So I'm going to put our part A down the bottom here. So we have these values here. What's going on? We have mass defect. If we can work out the fact that there is a drop in mass from the reactants to the products, that mass defect will result in energy due to E equals mc squared. Now, because it's in atomic mass units, or U, then we can easily convert it into the energy by simply multiplying it by 931.5 mega electron volts over c squared. In other words, that is actually the conversion that you need to convert it to mass in terms of mega electron volts per c squared, and then just drop the c squared to get the energy. Let me go and explain that. So first of all, let's work out the mass defect. We obviously have 238.0495, and we have to subtract the product, which is 234.0409 plus 4.0026. Now, when you calculate that out, you're going to get 0.006. So there is our mass defect. Now, our energy, therefore, will be simply that U value, which is 0.006, and we simply multiply this by 931.5 mega electron volts. That will give us the actual energy. And so when we calculate that out, we're going to get 5.589 mega electron volts. But hold on, we're given a value here of joules. How do we convert that? Well, all we need to do is, this is our mega electron volts, so we need to convert this to electron volts, and then when we multiply it by 1.6 by 10 to the negative 19, we get our answer. So in other words, what we have is 5.589 times 10 to the power of 6, that allows for the mega, and then multiply this by 1.6 by 10 to the negative 19, and when you do that calculation, you're going to get 8.94 by 10 to the power of negative 13 joules, and you'll see this, if we round this up, we'll get our 9.0 by 10 to the power of negative 13, which of course is the answer that we're looking for. Now let's have a look at part B. We're saying, well, at launch, the generator contains that many atoms, and the half-life is that value. Calculate the total energy. So what we need to do is, first of all, look at how much we have lost. In other words, this nuclear decay, and so we start off with a certain value and we need to know how much is lost. If we work out how much is lost, or at least how much is remaining, and therefore we know how much is lost, we know that for every single loss is the energy that we just calculated earlier. So the first thing is to do that. So we know the formula for our half-life is n0 e to the negative lambda t. Now what is lambda? That is the decay constant, and our decay constant is equal to our natural log of 2 over the time in half-life. So we can substitute this in, and so we get 0.79. Now we can substitute this in. Now remember, we're starting off with 9 times 10 to the power of 24. We multiply this by e to the power of, now it's negative. Now we're putting our decay constant in, so we get 0.0079. Now in this case, the time that we have is in the first 10 years, so we're just going to put our 10 value in here, and when we calculate that out, we're going to get 8.316 times 10 to the power of 24. Now this is left over, so what we need to do is how much we've lost. So therefore the loss is simply the difference between those two, and we get that value. Now we know that that's how much we have lost. Of course, therefore the energy as a result will be this value multiplied by this value. So therefore the total energy will be equal to 6.836 by 10 to the power of 23. We multiply this by our 9.0 by 10 to the power of negative 13, and the total energy ends up being 6.153 by 10 to the power of 11 joules. And that's the energy produced in the first 10 years. So that is the HSC for 2021. I hope that has been helpful for you. Please like, share and subscribe. Make a comment down below if this has been helpful for you, and please consider supporting me by buying me a coffee. The link is in the description below. My name is Paul from Physics High. Take care and bye for now.